Hello students, here is your next calculus lesson. I think this is notes number 33 and the title is the second derivative test. So let's review a little bit. 2 lessons ago you learned the first derivative test. We're going to talk about that today as a refresher, and then we're going to learn the second derivative test. Last lesson you learned about concavity, so you learned what it meant for a graph to be concave up or concave down and how that relates to the second derivative of the function. So we're tying those ideas together. Okay, what is the first derivative test from 2 lessons ago? The purpose of the first derivative test is to identify local maxes and mins. We could call those local extrema. Now, how do we do it? What's the process? So the steps for the first derivative test are that you find the critical points. Remember, those are points that make the derivative equal 0 or not exist. And then you establish intervals around those critical points. And then you pick a test point in each interval and you determine if the first derivative is positive or negative in that interval. And based on those sign changes, you can identify whether you have a max or a min, or neither. Look at sign changes to draw conclusions. Remember that if your graph goes from having a positive derivative to a negative derivative, that means the graph is increasing and then decreasing, f prime positive, f prime negative. That means you have a maximum. But if your graph goes from having a negative derivative to a positive derivative, that means it's going from decreasing to increasing, f prime negative, f prime positive. That means you have a minimum. Okay, local max, local min. So now let's talk about the second derivative test. The purpose of the second derivative test is exactly the same. People get confused about this. Same purpose as first derivative test. That is to identify local extrema. It's a different way to do the same thing. In some cases, it's a much faster way to do the same thing. In some cases, it's not faster. So you'll get to decide sometimes whether you want to use the first derivative test or the second derivative test to identify local extrema. Here's what you do. Start out the same way. Find the critical points. Points where the derivative equals 0 or does not exist. Then you plug your critical points. Plug is, of course, a very sophisticated term. Plug critical points into second derivative. Here's why we do that. We learned last time that if the second derivative is positive, you are concave up. Your graph is concave up. So f is concave up when f double prime is positive. And if you're looking at a critical point and you're wondering if it's a max or a min, and if the graph is concave up, then you must be at a minimum. And we also know that when f is concave down, f double prime is negative, and if you're looking at a critical point and your graph is concave down, you must be at a maximum. So you're going to take your critical point, plug it directly into f double prime, and then you look at the sign, basically. Look at sign of f double prime of c. If we call the critical point c, look at f double prime of c. If f double prime of c is greater than 0, so positive, that means the graph is concave up. That means you have a local minimum. If f double prime at your critical point is less than 0, that means it's negative, so the graph is concave down, so you have a local maximum. So here's the advantage of using the second derivative test. You don't need intervals, so you don't need to test two things. When you use intervals, you test two things, below the number, above the number. When you're plugging the critical point directly into the second derivative, you're only testing one thing. Here's the disadvantage. You have to find the second derivative. Sometimes, for some functions, that's going to be really messy and complicated, but for other functions, it's not going to be. Sometimes you have to find the second derivative anyway, because you might be doing a whole bunch of things in the problem, and some of the things require you to find a second derivative. Okay, we're going to work through some examples, and since we're keeping these lessons short and just kind of touching on the essentials, my examples are not super complicated, and my homework assignment is not very long, but the hope is that you will understand the concept, even if you're not practicing it with all kinds of extreme problems. Okay, number 1, find the critical points and apply the second derivative test for f of x equals x to the 5th power minus 5x to the 4th. So when it says apply the second derivative test, we're going to figure out if we have local maxes or local mins using the second derivative test. To find the critical points, we take the first derivative, and that would be 5x to the 4th minus 20x cubed, and we see where it equals 0 or does not exist. Since this is polynomial, it always exists. Let's just see where it equals 0. Let's factor 5x cubed out of both terms. So we have 5x cubed times x minus 4 equals 0. Set each of these equal to 0. And we end up with critical points x equals 0 and x equals 4. So what we want to know is, do we have a maximum? Do we have a minimum? What's happening at 0? What's happening at 4? So if we were doing the first derivative test, we would make intervals now, and then we would test each interval. But we're doing the second derivative test, so we need to find the second derivative, and that would be 20x cubed minus 60x squared. See, for this problem, when you have a polynomial, finding the second derivative is a piece of cake. So it's a great time to use the second derivative test. Okay, now we're going to take our critical points one at a time and plug them in. So f double prime of 0, 20 times 0 cubed minus 60 times 0 squared is 0. Uh-oh, we have a problem because the second derivative test said if you get a positive, you have a local minimum. If you get a negative, you have a local maximum. It didn't say what to do if you get 0. So we're going to have to come back to that. Let's do f double prime of 4. F double prime of 4 would be 20 times 4 cubed minus 60 times 4 squared. And for that, I get 320, and 320 is greater than 0. So that means the second derivative is positive at 4. That means the graph is concave up at 4. That means at 4, we have a local minimum. Now, what are we going to do about 0? We can't avoid it anymore. If you get 0 from using the second derivative test, we say the test fails. And if the test fails, guess what you get to do? The other test. What's the other test? The first derivative test. So let's do that. So that means we need to establish intervals around 0. So we have negative infinity to 0. I'm going to label this the first derivative test. In fact, I would always encourage you to label your tests. Over here, this was the second derivative. Hopefully, when you're labeling them, you can actually read the writing. With the tools I have at my disposal here, it's not so clear. Okay. So now we're doing the first derivative test. We're forced to. Intervals around 0. Let's pick a number in the interval. Let's test x equals -1. Let's test x equals 1. And we're testing those into the first derivative. And so when we take -1 and we plug it into the first derivative, here we go. Here's a factored form of the first derivative. 5x cubed would be negative. -1 minus 4 would be negative. Negative times negative would be positive. Let's plug in 1. 5 times 1 would be positive, positive, and then 1 minus 4 would be negative. Positive times negative would be negative. Okay, so what does that tell us? That tells us that we have a graph f that's going from increasing to decreasing. So we have a local maximum. At x equals 0. Okay, there we go. Let's try another example. Number 2. Find the critical points and apply the second derivative test for f of x equals x cubed. If you want to, you could pause and try this yourself and then check and see how you did. So we start by finding the critical points. Take the first derivative. That would be 3x squared. Set it equal to 0. And you end up with x equals 0 for your critical point. And for the second derivative test, we find the second derivative, which would be 6x. To plug in our critical point, plug in 0. Oh no, it's happening again. We get 0. Test fails. What good is this test? It keeps failing. Oh, well, so I keep giving you examples where it's failing because I cut out all the other examples because we can only do so many examples. So now we're going to do the first derivative test. So let's go ahead and make intervals. So we have negative infinity to 0, and we have 0 to infinity. Let's test x equals -1. Let's test x equals 1 into the first derivative. If we take -1 and square it and multiply it by 3, we get a positive. And if we take +1 and square it and multiply it by 3, we get a positive. So this graph is going from, f of x is going from increasing to increasing. It does not have a local max or min there. And I hope you realize that that is what f of x equals x cubed looks like. Maybe you even thought about that before we started. The cubic graph doesn't have a max or a min, a local max or a min. It's actually an inflection point there. Okay, so we'll just say x equals 0 is not a max or min. Okay, let's take a look at the next one. Number 3. Find the local extrema, intervals of increasing, decreasing, inflection points, and intervals of concavity. Oh my goodness, that's a lot to do for this cubic function. Use all of the info to roughly sketch the graph. Okay, sure, we can do that. So we need the first derivative. What do we need the first derivative for? For the local extrema, the intervals of increasing and decreasing. So let's go ahead and find f prime of x, and that would be 12x squared plus 24x minus 36. Let's set that equal to 0 to find the critical points. I'm going to factor out a 12. 12 times x squared plus 2x minus 3 equals 0. Does that factor x plus 3 times x minus 1? That's convenient. Set each of those equal to 0. And we get x equals negative 3 or x equals positive 1 critical points. Okay, now to figure out if those are local extrema, we could do the first derivative test or we could do the second derivative test. Second derivative is going to be easy to find. We need to find it anyway. But we also need to know the intervals of increasing and decreasing, so we're going to have to do that anyway. So we're going to have to do everything anyway. Let's go ahead and carry on with the first derivative and find the intervals of increasing and decreasing. So we have the interval from negative infinity to negative 3. We break the intervals at the critical points. We have the interval from negative 3 to 1 and the interval from 1 to infinity. Let's pick a number and plug it into the first derivative. I'm going to pick negative 4. So I have 12 times negative 1 times negative 5. Positive times negative is positive. For the next interval, I'm going to pick 0. So I have 12 times 3 times negative 1. Positive times negative is negative. For the next interval, I'm going to pick 2. So I have 12 times 5 times 1. Positive times positive, that's positive. So what does that tell us about f? F is increasing, decreasing, increasing. F increases when the derivative is positive, f decreases when the derivative is negative. Now we have enough information to call this the first derivative test and to make a determination about our critical points. So x equals negative 3. It's going from increasing to decreasing, so we have a local maximum at x equals negative 3. And the next section is going from decreasing to increasing, and that change is happening at x equals 1. So we have local minimum at x equals 1. Okay, I'm putting a box around everything we're trying to find. We just found the local extrema. We found the intervals of increasing and decreasing. Those were associated with these intervals up here. I'm not going to write them again, I'm running out of room. Now let's find the inflection points. What are inflection points? Inflection points are the points where the concavity changes. How do you figure out the concavity? The second derivative. So let's find the second derivative now. F double prime of x would be 24x plus 24. Let's see where that equals 0 or does not exist. Okay, there's nowhere it does not exist, so let's see where it equals 0. Let's factor 24 out of that. Set that equal to 0, we get x equals negative 1. Is that a critical point? Sorry, no, it's not a critical point. That's not what I meant to ask, but the answer to that is no. Critical points are numbers that make the first derivative equal 0 or not exist. What do we call the numbers that make the second derivative equal 0 or not exist? Do we call those inflection points? No. They might be inflection points. They are potential inflection points. PIP, that's my word for it. Remember PIPs? Potential inflection points. We don't know if it's an inflection point until we see if there is a change in concavity. So let's check out the concavity. So let's make intervals. We have the interval from negative infinity to negative 1 and the interval from negative 1 to infinity. Let's take a test number and plug it into the second derivative. So I'm going to pick negative 2. If I plug negative 2 into the second derivative here, I have positive 24 times negative 1. Positive times negative is negative. And now I'm going to pick, for the second interval, I'm going to pick 0. And plug that in here. 24 times 1 is positive. So what does that tell me about f? When f double prime is negative, f is concave down. And when f double prime is positive, f is concave up. Do I have a change in concavity? Yes. Do I have an inflection point? Yes. X equals -1 is an inflection point. Okay, so going back to the directions, we got the inflection points, and we also got the intervals of concavity, concave down, concave up. Use all of the info to roughly sketch the graph. Okay, this is a lot of info. So, here's what we're going to do. First of all, we have some x coordinates. Let's find their y coordinates. So we had the important point that was a local maximum, -3 something. Let's find its y coordinate. We had a local minimum, 1 something. Let's find its y coordinate. And we have an inflection point, -1 something. Let's find its y coordinate. Find the y coordinates by substituting the x values into the original function. So I used my calculator, and I used the table feature, and what I got for -3 was 108. For -1, or for +1, I got -20. And for -1, I got 44. Okay, so we're going to plot those points. We also know that the graph is doing things like increasing and decreasing, concave up and concave down. I'm going to make a new interval list that has breaks at the critical points and has breaks at the pips. So we have -infinity to -3, -3 to -1, -1 to 1, and 1 to infinity. So that kind of is going to combine both of the interval sets of interval work we did in the previous part of the problem. What is f doing from -infinity to -3? It is increasing and it is concave down. What is f doing from -3 to -1? It is decreasing and it is concave down. I'm just looking back at the previous work and putting it in a new chart. What is f doing from -1 to 1? It is decreasing and it is concave up. What is f doing from 1 to infinity? It is increasing and it is concave up. So we need to make all of that happen. Okay, here we go. Let's say this point up here is at a height of 108. Down here we're at a height of 44. Down here we're at a height of -20. I don't have the luxury of really making this perfect. We have x values that matter at 1, at -1, at -3. Okay, let's make our graph increase. Oh, let's put our points in place. -3, 108. -1, 44. Let's put our y-intercept in there. What is our y-intercept? It's 0. And we have 1, -20. Now just imagine if we had time, we could combine this with what we learned last year in pre-calc about where the zeros are, and we could have an even more thorough investigation of this function. Okay, for this interval here, we're going to make our graph increase and be concave down. Okay. For the next interval, we're going to make our graph decrease and be concave down. Okay. For the next interval, we're going to make our graph decrease and be concave up. All right. that curvature change so it looks more like a bowl and less like a mountain. And then for the next interval, we're going to make our graph increase and be concave up. All right. Now, did we end up with a local maximum at -3? Indeedy, we sure did. And did we end up with a local minimum at x equals 1? Yes, indeed we did. And did we end up with an inflection point at x equals -1? Looks like a concavity change to me. So that worked great. Okay. Now, I don't think that I can spend the time on this example because I'm already at 25 minutes. So maybe I'll make it a separate video and you can watch it if you have time. And the homework, page 239, 25, 27, 29, 39. Thank you, everybody.